Now we will demonstrate the least square classification in the following 4 different setups. In the first setup, we will use a binary classification setup where classes are linearly separable. In the second setup, we will add a few outliers to the linear separable binary classification setup. In the third setup, we will use multi-class classification with number of classes equal to 3. And in the final setup, we will be using a least square classification to classify non-linearly separable classes. And there we will be using polynomial transformation for learning the nonlinear decision boundaries. So let us create a binary classification setup with number of samples n is equal to 50. So this particular function create.dataset also has facility to add outliers to the generated dataset, and it can also generate samples from multiple classes. So if you want to add outliers, you have to set add outliers to true, and if you want to add more classes, you can set add class equal to true. Then it will generate setup with 3 classes. We will first perform generic data preprocessing on the generated dataset. So we'll generate the dataset, we perform polynomial transformation. By default, degree 1 on feature set. We divide the data into training and evaluation set with train test split API from sklearn library, and we perform label transformation for both training and test set. And as we discussed earlier, label transformation is one of the most important aspect or most important implementation step in least square classification, or for that matter in any other classification algorithm. So you can see this data preprocessing function. We first create toy dataset, we perform polynomial transformation on the feature matrix with the specified degree, and by default the degree is 1. Then we perform the training evaluation split using train test split function. Then we perform label transformation on training as well as test labels, and we return the training and test or evaluation feature matrix label sets as well as transformed label sets. We can visualize, we also write the code for visualizing the model as well as the dataset. For model visualization, what we do is we generate a test set from by using the MeshGrid function and generating points which are uniformly sampled between the min and max of the feature 1 and feature 2, and we sample about 100 points. So we have test set of 100 points. We perform the polynomial transformation on this test set, and we send this transform feature set for prediction, and that's how we get the labels. And using this test set, we essentially visualize the classification boundary. So we first call the preprocessing function that generates linearly separable binary classification setup for us. You can see that there are 37 examples or samples in the training set and 13 samples in the test set. Each sample, and there are essentially 3 features. There are 2 features plus 1 dummy feature, so including dummy feature there are totally 3 features. And we see that the first dimension of the shape matches for training as well as label vector as well as test feature and label vector, so which is a good sign, and that shows that the data is loaded or data is generated properly. Next, we can visualize the data. You can see that there are 2 classes, class 1 which are orange dots and class 0 which is blue dot, and our job is to come up with a classification boundary that separates these two classes. So we instantiate least square classification object, and we try to learn this decision boundary through normal equation as well as through iterative optimization. So in order to learn it through normal equation, we simply call the fit function with the feature matrix and the transform label set, and we also set up, here we have set up regularization rate equal to 0, so we get a standard least square loss function, and based on that we perform the fit. And if you visualize the model, you can see that we have learned a boundary which is a line which looks something like this, and there are certain points from class 1 that are right on the boundary, and there are a few points that are misclassified. So when we perform iterative optimization, we also look at learning curve, because iterative optimization fits the weight vector by performing iteration over the training set. Iterative optimization methods updates the weight vector in each step based on the gradient of the loss function and the learning rate. So in order to make sure that the training is performing as per expectation, we tend to look at the learning curve. So first, we'll train the model with SGD or stochastic gradient descent and examine the learning curve. So we simply call the SGD function of the least square classifier object, and we train SGD for 100 epochs, and you can see the learning curve, and you can see that overall the error is going down, or the loss is going down as we perform more and more iteration. And you know, the kind of oscillations that you see in the loss is kind of common for SGD. All that we have to see is that whether loss is going down gradually. And we can see the decision boundary learned by SGD classifier, which is very similar to what was learned by the normal equation method. We can also perform gradient descent, and you can see that when we perform gradient descent with number of epochs equal to 100 and learning rate of 0.0001, you can see that the learning curve is pretty smooth, right? So as the training progresses, the loss gradually comes down. And finally, we get a weight vector, which is essentially which is same as what we see in normal equation method, right? It is 0.54, 0.45, and then you can see that then there is 0.25, 0.12, and there is a negative of that here. So you can see pretty much similar setup, right? So here, so the weight vector that was obtained with gradient descent and fit and the normal equation method, they match pretty closely, right? So this first column is the weight vector corresponds to the first class, and is the weight vector corresponds to the second class. And each weight vector has three components. The first one corresponds to the bias, the second one corresponds to the first feature, third one corresponds to the second feature. And you can see that this model is also pretty similar to what we obtained from the normal equation method. Now let's compute the evaluation matrix. So first we calculate the number of true positive, true negatives, false positives, and false negatives. And then you can actually plot them in confusion matrix, and based on these four quantities we define precision, recall, accuracy, and F1 score. F1 score is indirectly dependent on them through precision and recall. So let's use these functions. So the true positives are the one where the actual value is 1, actual label is 1, and the predicted label is also 1, that is true positive. True negatives are the ones where actual label is 0 and predicted label is 0. When actual label is 0 but predicted label is 1, it's a false positive. And then when actual label is 1 and predicted label is 0, it's false negative. It is predicted to be negative but in a false manner. That's how we read it, and we have discussed this particular concept in the first week of our machine learning techniques course. Now precision is simply the ratio of true positive to true positive plus false positives. Recall is ratio of true positives to true positives plus false negative. Then we have accuracy, which is true positive plus true negatives divided by sum of all these 4 numbers. And F1 score is calculated as a harmonic mean of precision and recall. Yeah, in this case we have perfect accuracy. So this is a perfect classifier that we came up with, at least on the test set. So looks like on test set we managed to get a good accuracy. Though on training, of course, we have seen that some points are misclassified. For example, this point is misclassified, this point is misclassified, and this point is marginally misclassified, whereas these 2 points are on the border. But on the evaluation set, it seems we are able to perform well, because it is likely that evaluation points are away from the decision boundary and in their respective class regions. Yeah, now what we'll do is we'll add a few outliers and see what effect we have on the decision boundary. We have exactly same setup, except that we have few more points here, because now we have 55 points. We added 5 outliers. So the training set has 41 points and the evaluation set has 14 points. So you can see that these outliers are added far away from the actual points, actual point cloud, where the points from class 1 are concentrated. And there are a couple of outlier points from class 0. They are also added away from the actual point cloud of class 0. And now, because of this outlier, the decision boundary changes significantly, right? So if you compare this decision boundary with the one that we had here, there's a drastic change in the decision boundary. And this is actually one of the problem with least square classifier, because least square classifier is quite sensitive to the outliers. So we actually got this boundary with fit function. If you try iterative optimization method, you will also find similar decision boundaries, and I would encourage you to perform that experiment and check the outcome. Next, we perform on multi-class setup with 3 classes. We simply have to call the preprocess with add class equal to true. That gets us an additional class. So we now have points from 3 classes, class 0, 1 and 2, and we perform the least square classification through the normal equation method. So we instantiate least square classification object, and we call the fit function on this, right? And remember, the label transformation happens in the preprocessing function, and once label transformation is done, the setup is generic enough that works on any number of classes. And you can see the decision boundary learned by the multi-class classification setup. And that decision boundary is shown in this particular visualization. And now you can see that there are 3 label vectors corresponding to each class. Now instead of calculating precision recall from scratch, we have used classification report API from sklearn.metrics library, and we simply have to get the prediction and send the predicted labels and actual labels to classification report, and we get the precision and recall for each of the class separately, as well as on an average using macro and weighted average. So we have macro average and weighted average precision, recall, and F1 scores. Finally, we have an interesting classification setup where the decision boundary between two classes is no longer linear. It is a nonlinear decision boundary. So we make use of make circles function in sklearn datasets API, and that basically generates points, something like this, where we have class 1 on the inside and class 0 on the outside, and they are separated by a circular decision boundary. Now, in order to learn the circular decision boundary, we use polynomial transformation, and we start with degree 2. And of course, here the problem setup is simple because we can visualize it since we are in two-dimensional space. But as as we are solving real life problems, you may not be able to visualize it. So in that case, I would recommend you to try polynomial transformations with different degrees, and then select the one on which you get the best accuracy on the eval set. So we need to do some kind of cross validation and in order to find out the right kind of degree of the polynomial transformation. In this case, it is easier because we could visualize it and we know that we need circular decision boundary. So we use polynomial transformation of degree 2. So remember this, and remember to practice cross validation in order to find out the right kind of degree for polynomial transformation. So we perform polynomial transformation and obtain a new representation for the training set. We perform the same transformation on the test set or eval set before applying or before calling the least square classifier on that set. And you can see that before transformation we had 2 features, and after transformation now we have 6 features. And there is, of course, these 2 features are copied as it is, plus there is one bias which makes it 3 features. Then we square up each of these features, which will get 2 more additional features, making it to 5 features. And we have one more feature which is the interaction feature between these 2 terms. So that's how we get 6 features from these 2 features. So we can look at the transformed. So this is the original feature space. This is the original feature space where these are the examples on the columns, on the rows. So you can see that from this example, right? So minus 0.96 and 0.24, we get the transformed representation. So we have one that is added by default, which is a dummy variable. We copy these 2 features as they are, and then we square this up and we square this up over here, and this particular one is based on the interaction of these 2 features. So this is how we transform each feature vector into a polynomial representation. Alright, now the next step is to perform a label transformation. We encode the labels, training label and test labels, and we visualize the training data. We have seen this earlier. Now we'll build a least square classification model. So what we have done already is we have already performed polynomial transformation. Now we will make an object of least square classification, and we call the fit function on the transform set. And when we call the visualize model function, we get visualization that you are seeing on your screen, where you can see a circular decision boundary separating 2 classes, class 1 and class 0. and we can evaluate the performance of the classifier using classification report. So this was the implementation of least square classifier from scratch, and we also demonstrated that on four different use cases.